morning. Usually if you've heard me present before, I usually start with some sort of story to help frame, contextualize this, but given the tight amount of time here, I was just plugging in, especially in OCP here, we have a lot of AI focus, and I thought about the fact of maybe getting AI to give me a pun for what I'm about to present here. So this is what Copilot mentioned about my particular presentation. So with our new OCP NIC feature, it's about time we synced up with the OCP timing appliance project. So let's make every second count. I thought that was pretty cute. So and basically that's what we're going to be talking about here is there has been today, and especially in the past presentation, a lot of advancements and efforts, especially here in the OCP realm, and especially here in the TAP group, on how we're being able to deliver and propagate time. If you've looked at what has been contributed up to this point, the timing card is something definitely, while it is not necessarily a high volume practical card that propagates traffic, it does propagate time. And what's interesting is when this was contributed a few years ago, we internally with my team, we talked about this. How are we going to be able to introduce high precision timing, not necessarily just to do it, but do it in a way where it scales. And when I say scales, we're talking about high volume, high revenue, impacting and changing the industries. And so I was really appreciative of this contribution, and especially to the OCP time server. Basically taking this time card, plugging it into a compute system, and being able to present something simple like 802.1 AS, IEEE 1588. And if you really want to get to more highly accurate time, unfortunately you're going to have to cable between the time card and a commercial off-the-shelf NIC. And in the time server project, I believe it was a CX6 that actually supported 1 pulse per second. And if you really want to get down to, say, G.8275.1 and .2, you're going to have to today leverage cabling to be able to propagate timing synchronization. And I'm going to show you today how that works in production systems, and talk about what the OCP NIC group just recently updated to help further scale this sort of solution. So there's two different ways to do it. You can cable internally. This one particularly was shown as an external cabling methodology. But like an internal cabling, there is a NIC out there today that actually supports internal cabling. They use U.FL connectors, this 50-ohm coaxial single-ended connector. They're very common in systems like Wi-Fi routers. If you were to open up your Wi-Fi router at home, you're going to see from the PCB these U.FLs routed from a very small miniature cabling up to the wand antenna. This is used on this particular NIC today, and it's a great way to route internal, well, let me say relatively great way to route internal cabling, but in really low scale numbers. So we're talking about like if you want to put a single unit together, a couple hundred, maybe just for a single network deployment. It's not such a bad thing to do, but when we're talking about real scaling, you have to think about the fact that people are going to basically factories, we're going to have to train people to actually plug the cards in, have to route these cables, and actually you're going to have to define and label these cables, very specific lengths. And it makes a lot of challenges in the factory, but honestly it's even more of a challenge in the field, because those same sort of instructions have to be presented, have to be debugged, diagnosed. Also with U.FLs, if you've not used them before, they're very miniature. They have low insertion rates. What that means is the number of times you can connect and disconnect. U.FLs are about 10 insertions, which if you're thinking about 10 to 10,000, in most cases that's just one shot to get that working. Otherwise you likely are going to destroy the connector on the NIC. And these NICs are not cheap. So that's a big challenge within something like this. It's not necessarily, like I said, it's good for like a low scale sort of thing. Not necessarily something you want to do in a ruggedized outdoor, semi-outdoor type equipment, but it can do the job. The other option, which is more used today, is external cabling. So this is an example of an Intel E810. This particular SKU actually has a GNSS receiver as well as a PLL and OCXO. It is compatible enough, it can support G.8275.1 and .2. This is an example I have in my lab where I took a Dell 1U rugged server, plugged both of these cards into the system, and we also, in discussing with various end customers, you know, the Vodafones, AT&Ts, the like, anyone that may necessarily use a system like this, cabling in this sort of scenario, they're going to want to be using aluminum-cladded SMA cables. And if you've ever interacted with these, and people maybe in the recording won't see my hands here, but here in the audience, you don't bend them. You have to shape them. And so on the first shot of messing with one of these 6-centimeter cables, I already cracked it. There's a very, even though it's aluminum, it's actually very thin. So I really want to present that because you have to think about that, yeah, there's probably a jig you can make to do more in higher volume, but it's still a very delicate process that, especially installers, you know, again, if you're thinking about thousands and 10,000s, there's opportunities where that external cladded jacket could be cracked, and that may introduce RF leakage within the cable. And that's something that may be very difficult to debug, especially when it's out in the field. So this is a kind of a further example of how this 1U rugged server would operate in a system. So generally, in a three-sector, 6-antenna structure, you're likely going to have at least a minimum of a primary mid-haul connection, likely a secondary connection if, depending on the location of where this particular unit is at. In this particular scenario, a slot 2 card would be the PHC. From there, you would use the SMA cables to branch down the 10 megahertz and the 1 pulse per second. And this is a deployable unit in the field. This is actually now live in many different systems out in the world. So it works, but again, it's not something of a desired item. When we looked at some of our customer satisfaction scores and talking with some of my other brethren from the system teams that also build similar systems beyond my company, this has been a challenge. It's also something that it also potentially locks you into kind of a single vendor. And so this is something that many of us on the NIC side of things have been discussing. So in the past year, we've been looking at not only areas where we're trying to expand in smart NICs. So last year we introduced a new capability. Instead of using the RBT interface, which is a 9-pin single-ended, it's basically an RMII bus. We were trying to transition to USB, mainly more for smart NICs, but it actually opened up an opportunity because what we're doing is basically the RBT bus is becoming legacy. We're trying to encourage a lot of the NIC vendors to move away from this 3.3 volt 9-pin interface and use the USB. I think it's going to help them reduce the cost on their particular NIC ICs, but it also presents us with an opportunity where as we introduce a new form factor, which is the DSFF, and recently, just this last month, we introduced this time synchronization feature. If you think about back with that Intel E810 card, it's basically a full height, half-length form factor. This DSFF is about the same size. If you've seen today's OCP NICs, pretty much all it can support is up to either 4 SFPs or 2 QSFPs and just the NIC IC. That's about all the space for it. But with this dual small form factor, there is actually opportunity that there's enough board area to replicate what could be done on that Intel E810 or a CX6 card. And so this is where, as we started introducing and defining this timing synchronization, what we want to do is, again, eliminate the need for cables, eliminate the need for internal or external aspects of it, and route it on the connector. So going back to thinking of the factory challenge, you're going to have a system, a chassis, a motherboard's put in, eventually the risers are going to get populated with this card. We're now eliminating that step of that cabling aspect of things. So we eliminated it in the factory, we eliminated it in the field. And so this particular feature has been introduced and released this past month over the summer. We went through and collaborated with many companies within the OCP NIC realm to define both an ingress and an egress path. So in both paths, you can have up to 3 pins, a frequency pin that can support EPPS, which is a combined 10 megahertz and 1 pulse per second. This is ideal for your PTP time reference, or it can relegate down to just 10 megahertz. And then a secondary pin where if you want to discretely have your own sync pulse, like 1 pulse per second for the PTP interface, you can use it that way. Or what a couple of companies brought up the idea of some networks actually need to have the synchronous Ethernet be on its own time domain. It's required in certain areas. And so this secondary pin can be 10 megahertz, and that would be part of your synchronous Ethernet timing structure. And then additionally, we also have a general purpose input from the NIC to the system. Mainly right now, it's defined as a loss of signal or a loss of lock, so that in theory, if you're provisioning your timing where maybe the primary is on one card, and if you have enough cards that the secondary can be on another card, you can move away from that particular card and move over to the redundant signal. The GPO is defined, but it's just, right now we don't have a specific feature for it. We want to at least have the provision of the pin. And there's also kind of an opportunity too where within it, you can also have, if some people have some vendor-defined ways, custom ways, you can actually define that within the EEPROM. So basically the motherboard will detect the OCP NIC. It'll determine through its free record, it actually supports timing synchronization. And then from it, it can start setting up the buses for it. Or if it just detects a basic, simple OCP NIC card, it doesn't see the C2 record, it can relegate down and just assume it's a non-timing synchronous NIC. And the way this all kind of looks out here too, now that the fact that the frequency and synchronous are on the connector and no longer on the cabling, so in this case, like what you saw in the earlier one, the OCP NIC of the first one could be the PHC. It'll propagate the frequency and the sync into the motherboard, and that motherboard can propagate it out to the particular NICs. The other thing too is PTM is something that, obviously we want to keep seeing that moving further. It obviously helps synchronize the PCI bus, but there's several people that think that if you can propagate that 1 pulse per second from the CPU to the NIC, you might actually be able to help further remove some of those discrepancies within the time deltas within that signaling. I presented quite a bit of information in about 15 minutes here, so I really appreciate y'all keeping up with me. Thank you very much. And I think that the thing that I really want some help with, so we defined the physical timing synchronization, so we have it at the physical level. Some of the next things we need to do is at basically at the DevFS and the PTP4L is how do we leverage this so that we can further scale this in a more interoperable way. This is something that I need some help from several folks from the NIC realm, and especially I'd like to hear from the TAP realm of what we want to be doing to make this more interoperable. Thank you.